Hi everyone, welcome to these Python tutorials where we are putting special emphasis on image processing. And before proceeding, I should just request all of you to sign up to appear.com, www.apeer.com, in case you want to look at or in case you want to use tools like for annotating your images or even using pre-configured workflows for image segmentation, whether it is semantic segmentation or instant segmentation using units and other advanced techniques. Now let's jump into this video. In the last two tutorials, we started talking about deep learning terminology in general, and we started off by scaling, understanding what scaling is, and in the next one, which was the previous one, we looked at activation functions. So today let's spend some time trying to understand loss functions. And these are very, very important and core component of neural networks. So let's make sure we take enough time to properly understand these loss functions. First of all, where do you define these loss functions? When you put together your model, you have to bring all the elements together, and we call that model.compile. Compile using what? Using a loss function, optimizer, and metrics to track. Okay, now we'll save these two for later, but let's have a quick understanding of what is this loss function, okay, and what type of choices do we have. So let's start by looking at the loss function itself. Now, first of all, think of what a neural network actually does. So think of a neural network as like a black box. In most cases, it turns out to be a black box, but by understanding these terms, we are unraveling each of these, so it doesn't stay a black box anymore. But think of this as a box where inputs are going in and outputs are coming out, right? So it's doing something in there. Now, what it is trying to do is it's understanding how the inputs are related to the outputs. So it's basically mapping. It's a function, non-linear function, of course, that maps your inputs to the outputs. If you have a linear function, y equals to ax plus b, you know how your y output is mapped to the input. It's a and b, right? Two terms. But with complex image processing or data processing, where you're fitting a neural network, this is highly non-linear way or non-linear function. But what it is doing is taking an input and fitting it to the output. So that's what a neural network does. Now it uses an optimizer to minimize the error in updating the weights. Okay, so we saw our neural network in the weights, and the weights are updated. Inside this box, you have neurons and that are connected, and between the connections, you have the weights. Each neuron value is multiplied by this weight and then adds the bias. Okay, so neural network, during the training process, it uses this optimizer, okay, to minimize an error by updating the weights. What do we mean by error? The error is nothing but your actual output versus the predicted output. So it's minimizing that error. Okay, in this, and there are various metrics to actually define this error. And this error is the function that defines this error metric is called the loss function or the cost function. So when we talk about the loss function, it is a function that kind of defines what is this error. I just mentioned to you what is the error in terms of an absolute value. When it comes to prediction, it is y true minus y predicted, right? That is your actual error. It's actually not just this minus that. We'll have a quick look at that in a second. It's typically referred to as the loss. The error that we are talking about is the loss. And the optimizer's job is to minimize this loss. And the loss function defines a function to quantify this error. Okay, now let's visually see what this means. So, what this means is, if you just look at these data points, let's look at linear regression. Is this the right line that represents this data? Or is this the right line that represents this data? To me, both look very similar. Now, to understand this mathematically, let's look at the difference between the actual data point versus the predicted data point, right? When we do a linear fit, all we are saying is, hey, this is my prediction of where the data should lie for a given x value. These are the y values, right? So that's what our line is. So let's look at what the error is. This is the true data point, and this is the predicted data point. So look at this error. I just described to you the difference between these two as y2 minus y1. But what if this data point lies on the other side, like on this side? then it is a negative value. On this side, this is a positive value, for example, okay, when you do y2 minus y1. So when you add all of these errors, they cancel out if it is negative and positive. So we square them. So we do squared of this error, y2 minus y1 square. So you just look at the magnitude of this and not just cancel out everything, okay? Now you have to add it for all of these data points. So we just do a summation of this. So it's basically y minus y2 minus y1 or y minus y prime or y hat whole squared. You sum them and you average them. So all this equation is saying is, hey, look at how the error for each data point, okay, and then square it and add all of those and take an average of those. That's it. This is nothing but mean squared error, which is the most commonly used loss function when it comes to regression type of analysis. So the goal of the optimizer is to minimize this loss function. So I hope you get a nice understanding of what a loss function is. What is the need for a loss function? It defines mathematically, so our algorithm can work with, the error in a given prediction. Okay, so now this is our regression type of problem. What if you have classification? If you say, okay, is this a nuclei, or is this not a nuclei, or is this a mitochondria, or is this a lysosome or something else, right? So you have a true value, but then you have the predicted values, right? So how do you do this for classification? So mean squared error obviously is not a right metric when it comes to that. It's a good metric for regression where you're predicting an absolute value, like what is the house price at a given location. So here you're not getting, okay, a cat or a dog, right? Here the output is, I don't know, 500,000 or a million or some number. That's a regression. When it comes to classification, the most commonly used loss function is called categorical cross entropy. Okay, and it's sometimes referred to as log loss because it's nothing but a logarithm of your probability, of your prediction right there. Okay, which is a probability for a given class. Now, if you only look at binary classes, two classes, this is called binary cross entropy, which is your C equals to 2, right? So it's basically C is the number of classes that you have. So if it's a binary cross entropy, value is 2. So when you expand this, you can actually see how the equation looks like. Let's not get into math. I just want to make sure you understand that for classification, cross entropy is a very common. There are much fancier versions of these, which I'll talk about one of those, which is my favorite, in a minute. Okay, so but let's summarize cross entropy. Cross entropy binary is for binary classification problem, and categorical cross entropy is for multi-class problem. And these are something you just type a letter. You're not going to code a lot of lines, to invoke categorical cross entropy. As you saw in the first slide, it's just, okay, you just name it, and oftentimes Keras actually library has this pre-built in. Otherwise, you can define your own custom loss function. That's a different topic altogether. So one thing I should mention is for multi-class problems, you need to encode the label as categorical. I'll probably again devote a video in terms of talking about categorical, but a quick summary in 30 seconds. If you have 3 classes, dog, cat, and a house, how do you provide that to the machine learning algorithm? You'll probably say, okay, this is 0, this is 1, and this is 2, right? 0, 1, and 2 for each classes. This is how we converted, how our labels were for random forest. But when it comes to machine learning, if you're trying to use categorical cross entropy, for example, or multi-class problems, you need to one-hot encode them, which means my 0 is not 0, it is 1, 0, 0. Because I have 3 classes, you have 3 numbers. And the first one, if it is 1, that means that belongs to the first class. So the next one, 0, 1, 0, that means it's the second class. And the third class is 0, 0, 1. Okay, again, that's a quick 30-second explanation, but we'll get to that in future. So a quick reference guide when you're using cross entropy, anything less than 0.05 or 0.2 is acceptable. It's good value. But any loss that's like greater than 0.3, cross entropy loss, 0.3 is not good. And if you're getting something close to like 2 or so, you're like, okay, that's pretty horrible. This is just a rule of thumb. Okay, now let's talk about one one modification of cross entropy that solves a specific problem. This is called focal loss. Okay, this is an extension, I should say, of categorical cross entropy. What does it do? Well, you can read this paper and understand this even better. But let's focus on this just one image in a minute. But in summary, focal loss is good for multi-class classification where some classes are easy and some are difficult to classify. What do I mean by that? For example, class imbalance, where you have like 90% of your data representing one class, but 10% representing the other class. Probably you can easily do a good job on this majority class in an easy way, but the minority class, you're struggling. This is where focal loss can really help. The other case, you probably have the same number of, let's say, pixels or classes for extremely bright class. We did this in our random forest example, okay? The mineral that has bright pixels, it was giving us great intersection over union values because it's easy to segment. It's all bright pixels. I can even use histogram to just do Otsu thresholding and segment that. But the one that has texture and very difficult to discriminate between, other minerals, it was a bit difficult to segment. So in those situations also focal loss can definitely help. Now why? We'll see that in a minute. It's like I said, it's just an extension of categorical or a cross entropy. And in summary, what it does is it downweights easy classes, easy to segment classes or easy to classify classes, and focuses the training on hard to classify classes. How does it do? Let's have a quick look at this image at a bit zoomed in. Now, what this image is telling you is on x-axis, you have the probability of this class. So if I have a cat and I'm saying that here, for that image, my probability is 0.2. That means I'm not classifying very well. Here, the probability is 0.8 for that image. Okay, that means I know very well what this image is. So I'm classifying that cat image very well if my probability is 0.6 or above, obviously, right? So when I give you something and I say the probability is 60% or above for that to belong to a class, you have a bit more confidence in that. So all this graph is saying is, hey, if the probability is above 0.6, we know with fairly high confidence what that class is. It's easy to segment. It's easy to classify. On the y-axis, we have loss. Remember, our goal is to minimize the loss. If we are not minimizing the loss, the training is focused on minimizing that loss. Okay, so now let's get to what are these different curves? Well, in focal loss, it's a function of a couple of parameters. One of them is gamma. If gamma equals to 0, your focal loss is nothing but your cross entropy. That's it, okay, if gamma equals to 0. So the blue line represents your cross entropy line. And as you increase the gamma, as you see, this curve is pushed more and more towards the lower end, okay? Now, how does this actually help us with anything? If you look at, again, my cat example, you have an image that you know is cat with a probability of 0.6. Or during the training process, it's looking at this and the probability is coming out to be 0.6. And if you look at the loss is about 0.5. Even though I have fairly high probability, my loss is pretty high. Why am I saying that high? If I go back to my cheat sheet here, anything 0.5 is kind of bad. It's not good. It's bad, right? So if I go back, now let's go back to this example. If you look at this cross entropy right there, 0.5 is bad. So the algorithm is trying to still minimize this loss and puts emphasis on this, even though we know it's easy to classify. Now, the same thing, look at the curve when gamma equals to 5, which is the green line. There, my probability or my focal loss value is 0.001. At the same position, your categorical loss, cross entropy loss is 0.5. Okay, that means if you're using cross entropy loss, you're wasting your resources trying to perfect something that's probably very close to perfection. But if you're looking at focal loss, the more emphasis is put on things that are not classified properly, right down here, versus the ones that are classified with fairly high confidence. That's the summary of focal loss without using much math. Okay, so Going back to the text I have here, focal loss increases loss for hard to classify examples, just like I mentioned. And in summary, focal loss turns the model's attention basically from these well classified examples to the ones that are difficult to classify. Okay, so that's focal loss. Now, let's jump onto our Colab notebook to again quickly look at each of these losses using one specific example. If things are not clarified, hopefully that should clarify any doubts you have. If not, again, use the comment section to initiate a discussion. So let's jump on to our Colab notebook. Again, please find the link to this notebook under the description down below. So please focus on the screen for now. So the first example we're going to look at is the mean squared error. And here I have defined three lists, which is actual, predicted 1, and predicted 2. Predicted 1 is very close to actual. Predicted 2 is slightly off in this case. Okay, and I'm just looking at our mean squared error, which is a pretty straightforward function to define. As you can see, for predicted 1, the mean squared error is 0.09, which is lower than 0.156, which is for the one where the prediction is slightly off. So during the training process, it looks at, okay, here are the weights, and what are the predictions, right? So initially it has, let's say our predictions are giving a mean squared error value of 0.156. And then it goes back propagation, updates the weights using back propagation. We'll talk about that in the next video, by the way, and updates the weights and does the prediction again. And this time the value is 0.09. It's like, great, it's going in the right direction. Let's update the weights, go back again. Oh, wrong direction. Let's go back and update the weights in the previous direction, and so on until it converges, right? Or until the number of epochs are reached. So this is your mean squared error. Now let's look at the cross entropy, binary cross entropy. And here is just something that we have written by hand. But in the later one, let's use a Keras example so we don't have to write every little line here. So the example I'm using here is, again, because this is classification, I'm just using zeros and ones. And for predicted 1, I'm using, oh, by the way, why isn't my predicted 0 and 1? Because when you do your outputs, right, when you use your sigmoid function, what do you get? Probability as an output. So it's never 0 or 1 unless you put some sort of a threshold where you say, oh, it's above 0.5, convert that to 1. Below 0.5, convert that to 0, right? But what you get out of a sigmoid is a probability. So that's why I'm using the value 0.1 to, as an output. 0.9. So as you see, all of these are very close to what the real classification is supposed to be. And predicted 2, I got some of them wrong, like 0.9 for, instead of 0. We'll print out how the results look like in a minute. And down here, this is just a function to kind of calculate our binary cross entropy. So let's go ahead and run this and look at the output. So if the actual is 0 and predicted is 0.1, our cross entropy is 0.105. And if the actual is 1 and predicted is 0.9, see, this is also 0.1 away from here. So the cross entropy is exactly the same. Now, where is the highest one? Right there. So our actual is 0, the predicted is 0.4, right? It's further away. So that's why I wish I had an example where the actual is 0 and the predicted is, so let's go ahead and print out predicted 2 instead of predicted 1. So let's just change this prediction to predicted 2, okay? And print out the results for predicted 2, because that's where some of these are quite off. Now you see 2.3 because the actual is 0 and our predicted is 0.9, pretty far off. So it's a very high binary cross entropy. That's it. Very as straightforward as it gets. Now, when it comes to Keras, there is a built-in library, for your binary cross entropy, as I already mentioned. So let's just use that to understand a multi-class classification problem. So here, my actual label I'm going to use is 3 classes, right? This list here, or this part of the array, is class 1, this is class 2, and this is class 3. We have 3 classes. So my predicted here is same as the original. I just want to see how, if I get 100% accuracy, how does my cross entropy values look like? And then I have 2 other classes, 2 other predictions. In one case, the prediction is class 1 is close to actual. Class 2 is 1 misclassification. Class 3 is 4 misclassifications, okay? And the other one is a bit more misclassifications right here. So let's go ahead and look at the average cross entropy. Let's look at this. And you see average cross entropy for PRID, which is same as our actual, meaning we have 100% accuracy. The cross entropy is 0. This usually never happens. And for prediction 1, for class 1, you see 0.15. Lower, class 2 a bit higher, class 3 a bit higher. Why is that the case? If you look at class 1, 3 misclassifications. We may have looked at a different, just a second, this one, sorry. Class 1, close to actual. Class 2, 1 misclassification. Class 3, 4 misclassifications. That's why we have small, medium, and high right there, okay, depending on misclassifications. Now, the loss is high for all of these classes, as you can see. And some of these classes are easier to classify. Again, I'm trying to build a case for our focal loss. So see the loss for class 2 in PRID 1, right? So if you look at PRID 1, loss for class 2, 0.603, which is very high value. But then if you look at PRID 1 class 2, right there, these values, if you look at the actual, this one is wrong, obviously. But then these two are 0.5, this one is 0.3, so that is correct, and this is correct. And these two are pretty close, like 0.5, but then this is slightly wrong, okay? Now, is there a way focal loss can help us with this? So now let's actually go down to focal loss. And again, we have written a few lines of code for focal loss here. Example is going to be pretty much the same, except let's only focus on PRID 1 to make sure we're not confusing too many things. So when we look at this, and prediction 1 is the same as we have used earlier. So let's go ahead and run this. And again, you can go through the code at your own time. But let's just look at the focal loss for class 1, class 2, and class 3. Okay. So class 1 0.08. Class 2 is 0.25, and class 3 is 0.54. So you can see that for class 2, the emphasis is lower. 0.2 is good, right? If you look at our, in general, cross entropy, or here, anything 0.2 is acceptable, 0.3 is not good, 0.1 is bad, and 2 is horrible, okay? And if you look at the cross entropy, like this is, we are looking at this class, right? Second class, this one, 0.4, 0.5, 0.5, 0.3, and 0.7. 0.4, 0.5, this one. So for that, we actually got 0.6 when you're only looking at binary cross entropy or categorical cross entropy, either way, 0.6, which is very high. But when you look at focal loss, it's telling me, hey, this is not very good, but at least put more focus on this other one, on this class 3. You see the difference here, 0.25 and 0.54. This is like 2 times already right there. Okay, so I hope this gives a good understanding of, again, you can play with these numbers, but actually let's go back. I was wondering why this is not too high. This is still very high. Sorry, let me trace back a little bit. This is 0.25, this is 0.54, and here what do we have previously? 0.6 and 1.3. These are exactly pretty much the same. You see, this is slightly above 2 times, right? 0.6 times 2, this is slightly above 2 times, these two classes. Now coming down here, this is slightly about 2 times right there. So not much difference when it comes to the difference between cross entropy and focal loss. The reason is I set my gamma to 0. When you set gamma to 0, that means your focal loss equals to cross entropy. That's why I'm not doing a good job. Let's just change this to 3. My gamma equals to 3. And now let's see if it makes any difference. Okay, so when we do that, now you see it's saying that, hey, my class 2 is working fine, so don't focus much on it. Class 1, we know that it's good, don't focus much on it. But class 3, put more emphasis on this. So as you can see, now look at the difference. Now my class 3 focal loss is 10 times higher, well, maybe 7 times higher, I should say, compared to class 2 focal loss. right? So it's putting that much more emphasis on class 3. So I hope I haven't confused you here. Again, let's take a couple of steps back. Cross entropy is giving us, again, it's not bad. It's giving us pretty good loss values for us to focus on each of these classes. But if you look at the first class, which is easy to classify, 0.15, the second class, which is a bit difficult to classify but still not that difficult, 0.6, and the third class is we are getting very bad results, so the loss is higher, so the network provides weights accordingly. But this class, we realized that is a bit easy. So why 0.6? Because 0.6 is very high. So is there a way we can change that? We realize that if our gamma equals to 0, it's behaving like cross entropy. But if I put my gamma equals to 3, it's now putting more emphasis, 7 times more emphasis on my class 3 compared to class 2. Okay, so this is why focal loss can be very useful for classification of data sets where you have one class that's easy and the other one that's a bit difficult. So I hope this summarizes the need for loss functions, what are loss functions, and what types of loss functions do we have, and what is focal loss. So in the next video, let's actually try to understand backpropagation, optimizers, which I hope really brings all of these elements together in terms of making some sense about neural networks in general. So let's meet again in the next tutorial. Until then, please do subscribe to this channel because you'll be notified as soon as that video gets uploaded. Thank you very much.